morning, everyone. So today we are continuing with the basics of the basic tools we need in general relativity. Today we are looking at the covariant derivative and also its property as related to the Christoffel symbol and the Riemann test. So very quickly, the definition of the covariant derivative for a scalar is simply just the ordinary derivative or partial derivative with respect to x mu as we are using it here. Now for a vector, or if we are talking about a covariant tensor, we have this to be its definition. So usually you have it to be, first of all, differentiate the whole tensor itself with respect to the coordinates x nu, then minus a contraction of the Christoffel symbol with the covariant index here, covariant index, and then I have the derivative nu and nu coming here as the indices for the Christoffel symbol. For a contravariant vector, of course, I will have that to be the p mu, the x nu, plus d plus gamma mu, and now I have the contraction of the lambda with one of these, but then the nu also combines with that. So these very two basic definitions give you the simplest that you will have for any covariant derivative. Now, of course, one of the very good properties we will have very clearly is to see that the difference between these two covariant derivatives when the indices are interchanged is simply the difference between the ordinary derivatives. Of course, like we've said, you could simply write p sub nu semicolon sigma, and this will mean differentiate the whole of p sub root nu, the x sigma, but minus the Christoffel symbol. The sigma here comes here. Now I know that I want to contract this index here, so I'm going to use something like lambda, a dummy index p sub lambda. Then the rho joins this Christoffel symbol. The same also goes for p sub sigma, and now I'm going to have the p sub sigma, the x rho, minus. Now what I'm going to have is a Christoffel symbol. Now what I have, okay, yeah, is a Christoffel symbol, so the sigma is here, and I want to contract it with this Christoffel symbol. So let's use something like, let's say alpha, and then I have here with me p, then I'm going to have a subscript of alpha, the rho comes over, and then the sigma, which was being contracted, joins this one. Of course, the difference between these two, like we've just worked out or written out there, p minus this, sigma dot, and so I'm going to have p rho semicolon sigma minus this object, that's this minus that. What I'm going to have in essence is the p sub rho, the x sigma minus the p sub sigma, the x rho. Of course, I'm going to have here with me minus of gamma lambda sigma rho p sub lambda minus, okay, so I'm doing this minus that, so this will simply be a plus, gamma alpha rho sigma p sub alpha. Okay, so looking at this, all I have here is a dummy index, and this is another dummy index. This Christoffel symbol with sigma rho here is symmetric with respect to the interchange of those two indices. So sigma rho here, rho sigma is all the same. So these two cancel. And of course, like we've said before in one of our lectures, this is a shorthand for what we mean by this. So by the p sub rho, the x sigma, we might as well use a comma to represent that. And also the same also with this. So we have just shown in a very simple way that this is indeed equal to that. Now let's go very quickly to the Christoffel symbol. The Christoffel symbol, as we have written it here, okay, yeah, well, this is a very good definition, but I have a very good mnemonic, I think, with which you can remember this. If you have a very slow mind or brain like mine, then maybe you will need it. But anyway, there are some situations in which it fails, so I want to make a distinction here. We could write this whole expression as this, gamma sub ABC, which is equal to that as that. Remember, the comma denotes a derivation, a differentiation with respect to x a. Another derivative with respect to x b would just be written with a comma. Then minus that. Now what's the mnemonic? The mnemonic means I simply write gamma sub ABC. Now I want to see this as some kind of cyclic permutation, or even permutation if you like. Simply have, I consider this as one of the permutations. So the next thing I'm going to write is G sub BC comma A. In other words, I do some sort of pushing that takes A back to the beginning. then I take a plus G, then I do some CA, comma B. Now you can see again as it goes. However, for the last one, I put a minus CB, comma A. No, I think that is. So what I'm going to have is AB, comma C. So apparently, of course, with a repetition of this order in the last one, it takes a minus sign. And this is what you have to be the Christoffel symbol. Now, supposing I decide to write my derivative instead of something like this, P, comma A, I write it as the A, P. Of course, this is still the same thing as we're differentiating with X raised to power A in this case, the P, the X raised to power A. And so the Christoffel symbol, which is here, written as this, also could be written as this. Now you can see that if you are writing the Christoffel symbol in this form, the mnemonic fails. It is no longer going to look like we had it or like I've been listening to. So you have to be careful if you are interested in this mnemonic on when and how to use this. Otherwise, you're going to be running into some serious problems. Now you can see in this case we have ABC. Well, you could say, okay, maybe we have some kind of BCA minus CAB. Anyway, whichever works for you, but I prefer this. This is the one I've been used to. You know what works for you. But it just tells you that we can, just by looking at the symbol, we can be able to write out what the Christoffel symbol is. Now, of course, it's a very simple exercise. I don't think, okay, maybe this is just to show that G sub AB is the same thing as G sub BA. So, in essence, if I have this formula or this one, if you decide, you can simply substitute C everywhere to be A. If we did that, I will have A here, and I will have A here. And like we said, BA, AB are the same. So these two terms will cancel. And by the way, C is A, so this here will be A. So I'm going to have some sort of G sub AA, comma B, with the half in front, and this is what it will be. So this gamma sub ABA is equal to that. Okay, now very quickly, we move on to the next thing, which has to do here with another definition of the Christoffel symbol. The Christoffel symbol, of course, again, could be written as this. Here, by raising one of the indices on the original one that we've defined, the index we'll be raising will be the one with the derivative, or the index of the derivative, or the independent variable with which we are differentiating. In other words, G mu sort of raises nu in this case to give us sigma on top here. Now, if we have this to be defined as this, then simply it means that gamma sigma lambda mu is equal to G, or maybe let me put it in the way that half G mu sigma multiplied by the G. Again, let me just go ahead with the short notation so you can see many ways by which you can decide to write this. Lambda mu comma mu plus G mu comma lambda minus G mu lambda comma nu. Again, so this is just one way by which we can define this. So in case you know already this variant, you can also define this other variant. And I guess this is most common. Now, of course, with this, we could also find another property that is very useful in applications, and that will have to do with contracting u and mu in this Christoffel symbol. By contracting u, mu, and sigma, we mean setting them to be equal. Now, since it's appearing once on top and once down, then we just go straight ahead, no need for any extra metric tensors. So I can write this lambda mu, and by the way, remember this is the same thing as gamma mu lambda. So since it's symmetric with the interchange of the lower indices. Now the next thing I'm going to have is setting it the same here as that. G, what I have here with me is gamma mu, and then I have G lambda mu comma mu plus G mu comma lambda minus G mu lambda comma nu. So I simply expand the whole bracket, open up the bracket. This is mu, G lambda nu comma mu plus half G mu, G mu comma lambda minus G mu lambda comma nu. This also has a half in it. Okay, so looking at this whole terms. Now you can see, for instance, that I have g sub mu lambda here, and g sub comma nu, and g sub lambda nu. Now the important thing here is I have this to be dummy indices, and they are both repeated twice. Now you have mu nu, nu nu. I have mu nu, I have mu nu. Now in one of these terms, I can simply make an interchange by interchanging mu and nu. So what I'm going to have is, here, this will simply be 1 over 2 g mu nu, g lambda mu comma nu, and then I have here with me plus the middle term g nu mu, g nu mu comma lambda. Now this is going to be minus half of g nu mu and g nu lambda comma nu. Okay, now looking at these terms, you have that this is exactly the same with this, except of course for the signs. So these two cancel. And I'm left here with gamma mu lambda to be equal to half of g mu, and then I have here with me g mu comma lambda. Okay, now this also could be written as half of g mu, of course, from one of our properties. Let me write this all out clearly. Yeah, that is what we have. Now I'm going to use a property from the book of Weinberg, his book on gravitational cosmology, principles and applications of general theory of relativity. It's chapter 4. I'll tell you the page or the equation number, but I prefer you read the whole chapter, or maybe better still the whole book. So you have trace here, like we've written it, no need to write it again, but I think you should just take a look. This is the expression. The expression says that the trace of the inverse of a matrix times the derivative of that matrix is equal to just the derivative of the mean, or you can say the log of the determinant of that matrix. Now, in this case, what we have to be a trace here is this Christopher symbol. We have mu's here contracted. That would be considered a trace in our own case. And also here, the determinant of our matrix. We know that the determinant of our matrix G mu is simply equal to G. So in other words, what we have here is something like this. So I'm going to exclude the two. G. So excluding the 2, I have here with me g nu mu. Well, it really doesn't actually matter. I shouldn't have bothered anyway, but the x lambda. This looks like the left-hand side here. And so if that is the case, what I'm going to have is this is the same thing as the x lambda mean of the determinant of my matrix, which is this. But I'm just simply going to write it as g, of course, which is what it means, by the way. Of course, in this case, if I decide, I may say that this is the same thing as 1 over g, the g itself, the x lambda. Now, in this case, what am I going to do? Or what am I expected to do or see actually in this? Now, I have that this is written as that, and then it therefore implies that my gamma mu lambda is equal to 1 all over 2, 1 over g, the g, the x lambda. This is what we have. Now, by a very smart trick, we can make this all look even more elegant, but still giving us a very good property that we will need. Can you see that this is the same thing as differentiating this with g, the x lambda? Because then, of course, if I want to express this, I'll simply have the 1 over g outside. Differentiating this with respect to x lambda, I'll have first 1 over 2 g raised to the power minus half. Then I'll have the g, the x lambda. Now, of course, this is the same thing as 1 over g out there. 1 all over 2 times root g. Then I'm going to have again the g, the x lambda. In the end, this is going to give me 1 over 2, 1 over g, the g, the x lambda. So you can see in that sense that what I have here is exactly equal to that. And this is a very wonderful property which we are going to be needing subsequently. And this is what we have here. Now, very quickly, applying what we've just shown right now. So let's look at the covariant derivative P mu lambda. Now the covariant derivative of this contravariant tensor we have stated before is the same as P mu dx lambda but plus. Now I'm going to contract this index, which by the way I'll move to the top of the Christoffel symbol. Let me use something like say beta, then comes along lambda. Now I have here beta. Now supposing I decide to contract mu and lambda, so that what I'm going to have finally will be P mu semicolon mu. So this is going to be the P mu on top here, the x mu, and I have here with me gamma mu, beta mu, P beta. Now this I guess looks familiar already. It's beginning to look like one of the results we already found, which is this. In other words, gamma mu, beta mu is all equal to 1 over the square root of g, and I have here the x lambda square root of g. Right? Now, with this illustration, what I'm going to have next, no sorry, I'm going to simply copy it because I'm looking at the index here, lambda and lambda. So this should be beta. Now with this illustration, we can see already that we can substitute this here. So that what we have here to be P mu is all equal to the P mu, the x mu, and I'm going to have plus of 1 over the square root of g, the x, beta, square root of g. And this whole thing here is multiplying P beta. Now this is what we have already from this expression. Now looking at this, we can see already that this will be combined in a more elegant way. Anyway, first of all, these are doubling this because they occur twice in our expression. So we can write this as the P mu, the x mu, plus 1 over the square root of g, the x beta, square root of g, and I have here with me, oh sorry, this was my attention, and put it down to the new thing. These are all dummy pieces that you said, so we can do that. In other words, this will be written as some sort of 1 over the square root of g, the x mu, into the square root of g mu. And that will give us that. Of course, you can see if we decide to go ahead with this expansion, one thing we could do is go ahead to expand it. By Leibniz rule, I will keep this a constant, differentiate this first, plus differentiate this, keeping this a constant. Now, if I keep this a constant, differentiating this, you can see that I end up with the left term here. And so the square root of g will cancel. Now, supposing I keep this a constant and differentiate this, that is what I'm going to have. So you can see in essence that P mu dash this which is exactly what is set out to do. So at this point in time, we can decide to look at the next expression. Sorry, we truly apologize for the buzzing sound you heard earlier. I'll take what I was saying again. So, taking down the covariant derivative of this vector, P mu with respect to sigma, what we are going to have is this, the P mu, the x sigma, plus the usual thing is we want to contract this index. So I use a beta, move the index mu, which was on top of P, on top of the Christoffel symbol. And now I have this to be written in this way. Now what we were trying to do was to contract sigma and mu. We simply just set them equal on both sides. So at this point, I make sigma equal to mu, and this is what I have here. On the right hand side, I have sigma here, so I turn it to mu. I come here also gamma mu sigma beta, so I have gamma mu beta. So I change the sigma here also to mu. Now what do I do next? I simply quote this result, which was what we obtained earlier in trying to operate with the Christopher symbol. Now in this case, since we have gamma mu with beta, what we have for this expression is that 1 over the square root of g times d dx beta square root of g times p beta. Of course, beta is a dummy index. To suit my purpose here, since I have mu, I can change the betas here both to mu. Now, having done that, I can combine the two into a simple expression like this. Or you can tell, of course, that this is the same with these two by just simply expanding this one. When you differentiate this using the Leibniz rule, you keep this one a constant, or let me say, yeah, keep this one a constant, differentiate this, then you have this cancelling that, and that's the first term. Plus, the next thing again is that I'm going to keep p mu a constant. I simply differentiate this, and now we have the whole thing here. So this is exactly the same as that, and it's a very important formula that we are going to be needing in subsequent operations. Now something follows directly from here. You can see I've written the covariant derivative of this tensor in terms of the tensor itself. Of course, maybe an ordinary derivative of the tensor itself. If this were to vanish at infinity or at the surface of your consideration in whatever calculation you're doing, if this were to vanish at infinity, then we'll have that this integral will be equal to 0. Of course, we are familiar with the Gauss theorem or divergence theorem in 4 dimensions. So you have that when you have the 4x, the mu v mu, that you have to be equal to this. Of course, in order to make this covariant, we'll have to multiply this with some square root of g. But that is if it is not already contained implicitly in your definition of this measure. In other words, what we have here is simply by the Gauss theorem, I can place my square root of g p mu semicolon here to denote a covariant derivative with respect to mu. This, by divergence theorem, is equal to that. So if p mu vanishes at infinity, it therefore means that any such integral as this is equal to 0, which is actually what we have here. Now that is one thing we can derive from this property. Now we have had this property also listed out here, which is what we intend to show. Now this tensor by the Christopher symbol is not a tensor, but well, this object multiplied with the metric tensor gives us something like this, which by our own method we said also lambda mu. You simply take this as one of the permutations. So I have next to be g mu comma lambda plus. The next will be nu lambda comma mu minus g lambda mu comma nu, and this is what I have. Now I could perform the same expansion for this, and this will give me that. When I add these two objects, I will have that these two terms cancel. This label with the same label, that's like labels 2 minus g lambda mu comma nu, g mu lambda comma nu. Of course, g mu lambda and g lambda mu are all the same. So this, for instance, cancels that. And also this also have the same like labels. This also cancels that. So we are left with these two terms. On adding, we simply obtain that to be that. So again, looking at this expression, we remember that the covariant derivative of the metric tensor g mu nu with respect to lambda is written as that. The usual thing, when we're differentiating this with respect to lambda, we have that you differentiate the whole object with respect to x lambda, then minus, since we're talking about covariant indices, minus, we perform a contraction of one of the indices with the Christopher symbol. So I have rho here, then lambda comes along, and the mu that was here moves also to join the Christopher symbol. Then multiplied by g sub rho nu. Minus this time, I want to contract the nu. So I leave the mu alone and move the nu to the Christopher symbol. Again, remembering that lambda is following me from the derivative, I perform the contraction again using the same lambda. Now I can put this in a bracket by saying minus this plus that. But recalling that this combination is the same as this which we obtained when we performed these operations. That's this plus that. Now looking at that, it therefore means that what we have here in general actually, which is the derivative of the metric tensor with respect to x lambda, you can see that G mu nu, the x lambda is exactly the same as this. So they both cancel. In other words, the covariant derivative of our metric tensor with respect to x lambda is equal to 0. Apparently, this is true also for the inverse metric tensor. In other words, in general, you know that when you have a combination of two tensors and you want to perform the combined covariant derivative of this object, then you will have to meet the Leibniz rule, the usual Leibniz rule apply, whereby you keep one a constant, differentiate the other, and then so on and so forth. Now, for the first case, we differentiate this, keeping this a constant, plus we keep this a constant, differentiate that. However, we have established that this is equal to 0. And if that is the case, then what we are left with this. In other words, the covariant derivative commutes with the metric tensor or the inverse metric tensor wherever it occurs. So whenever you have such a combination as this, and you have a semicolon outside of this, it's fine to just write it as that. Now, the next thing we are going to be looking at is one of these tensors, also which we try to explain here. We want to derive that formula very quickly. Hopefully, we can do this in the short amount of time we have. So, what we do next is the covariant derivative of this is the usual thing, the F mu nu, the x sigma plus. Now, I want to contract one of these indices, mu and nu. And I'm choosing mu this time. So, I move mu to this point, just at the same level, bring down the lambdas, this is the contraction. I'm differentiating with respect to x sigma, sigma is here. So I have f lambda nu, plus this time around I leave mu alone. I want to contract nu. So I now contract it using another index. Well, I could maintain lambda or whatever, but I just choose to use rho this time around to use the contraction. However, the one with which I'm differentiating with respect to continues to remain at the ground or maybe as a subscript for the Christoffel symbol. And then the nu that I'm contracting moves to the Christoffel symbol. Now, supposing in this expression, as it's written, I want to perform a contraction of sigma and mu. What do I do next? I simply just change sigma everywhere to mu, both left and right hand side of the equation. I do that here on the left hand side, I have mu here. Here also I have mu, and here I have mu. It goes on, and yeah, exactly. So wherever there was sigma before, I change it to mu. Now, looking at this last term, I think that is a little bit of interesting. To avoid any confusions, but just this last term. That last term over there is exactly as this. If we assume, or if f mu nu is antisymmetric in mu and nu, in other words, when I perform this operation, f mu nu is the same thing as minus that. That's what I mean by antisymmetric in mu and nu. Now, this whole object combined together, I could perform an operation that says interchange mu and nu. Wherever I see mu, I change it to rho. Sorry, and whenever I see rho, I change it to mu. I can do that because they are all dummy indices, and there will be no sign change in this case because all I'm doing is changing dummy indices, one dummy index to another. However, if I perform an operation on this object alone by just moving mu to replace rho and rho to replace mu, I get a minus sign because that's the essence of this property. Now, having gotten a minus sign, I could again naively perform the change of every dummy index to another. That is, I interchange mu and rho all over again. If I did that, what I'm going to have in this case will be rho changing to mu and mu changing to rho. I come over here again. Sorry, I didn't perform that in the way that it should have done. So I change this the first time. I get a minus sign. So I perform another change for all of them again. And what do I have? I have here to be rho mu. And of course, what we have done actually isn't nothing. Okay, so the change here was supposed to have been here, right? So I have here gamma. Yeah, everything changes to rho, and then mu. Then I perform a change here also to give me that, which gives us a minus sign. Then I go back again and I have rho, I have mu. Then here, what do I have? I have another mu here and I have rho. It's all good and well. All over again. So, well, this is all just very straightforward. Please don't get confused with this. What it means again is that I can decide if I want perform the interchange of rho and mu. In other words, this is the same thing as minus this rho mu, f rho mu. However, this is symmetric with the interchange of rho mu for the Christoffel symbol. If I perform that operation, I'll simply be obtaining here finally minus this mu rho f rho mu. The essence of this whole operation is we have shown that this object is equal to minus itself. Please, if you got confused with this, you can just go through what I've said again or maybe look at it again. So in essence, this expression, this last expression is 0. We can simply just drop it. And this is one thing we have gotten from the contraction that we've performed. So we can drop it. And now the next thing we are looking at is simply this term and this term. And that's what we have. So if this is equal to 0, we are left with this contraction equal to simply the first term plus the second term. Now what do we do next? We simply put our result for this. And we have obtained this and used this at least twice now. So at this point in time, this is the same as that, remembering that there is a single or a free index here, lambda, which follows us in this derivative. However, lambda here is a dummy index, so I have the freedom to change it to mu, because that's what I want to. I want it to just have some similarity with the first term. If I did that, I will have f mu nu here, and then the x mu. Everything looks good. And of course, you can see that these two terms can be combined into this. Just by what we did for the case of P over there, what you have here. So for P, you can see we have this plus this to give us that. And the same thing applies here. So if I were to treat this by Leibniz rule, keep this a constant, differentiate this, this is the term I get. Plus I differentiate this one, keeping this one a constant, and that cancels that, and you get the first term here. So this is what we have for this one. Hopefully the other property we are going to be looking at, but may not necessarily show, is that the summation of these covariant derivatives all gives us the same derivatives, but this time changed to ordinary derivatives. So all the semicolons change to commas. All this will have to do is with a simple illustration of substituting the full expression of this and making use of the fact that f mu nu is antisymmetric. So by doing that, all the unnecessary gamma terms cancel, and you're left with this alone. So at this point in time, I hope this wasn't too bad a presentation because of the buzzing sounds. So let's look at the next skills that we need in general theory.